Our next talk presents a general mechanism in type system design inspired by modal logic. This work is called A Unified View of Modalities in Type Systems, and it is a paper by Andreas Abel and Jean-Philippe Bernardi, both from Gothenburg. Jean-Philippe Bernardi will be giving the talk.
Hello and welcome to A Unified View of Modalities in Type Systems. My name is Jean-Philippe Bernardi and this is joint work with Andreas Abel. Modalities are qualifiers that modify types or propositions. For example, in the sentence, "It may rain today," the "rain today" proposition is qualified with the possibility modality. Another possible example is the qualification of propositions by the agent who believe it, as in, John thinks that it rains today. In programming languages, it can be useful to qualify a type by an amount, representing how much is available. For example, 5.543 millimeters of rain. Another useful kind of qualifier is whether information is public or secret. In this work, our goal is to describe a system which unifies all such instances of modalities. We also want the system to have a useful meta-theory, which all instances can inherit. Our work is set in the framework of System F, also known as the polymorphic lambda calculus. I am going to assume familiarity with it. Also, I assume you know that they are isomorphic. If you watch this video offline, feel free to pause and read the slides at your own pace. Or you can consult the paper and come back later here. As suggested by the examples that I've shown above, we add a new type form a P boxed A, which I will just read out PA in the future. This means A qualified by modality P. To support model types, the key idea is to annotate every type variable, or every variable, with a modality in addition to its type. Again, to support model types, the key idea is to annotate every variable with a modality in addition to its type. Formally, what we do is to change the judgment so that it includes this little gamma here. It is a map from variable names to modalities. An important thing to note is that the resulting type A in the judgment has a unit modality. This unit modality will be interpreted differently depending on the application, but I can already say that it acts as a default modality. To produce A with another modality, say PA here, we need to multiply the modality context by P. That is, we multiply every modality in the context by P. In the same vein, if we want the product of A and B, then we need the sum of their respective modality contexts. To see how this plays out, let us first look at a fragment of plain system F without modalities. Then we can see how modality annotations get added. Let's look first at the variable rule. What it says is that A is used exactly once, and so A is annotated with the unit modality in the context. Also, that the rest of the context is not used at all, and so it is annotated with the zero modality. For consistency, we also annotate the domain of the hour type with the modality. You can see how this plays out in the ABS and AP rules, abstraction applications. In particular, in the application rule, to be able to feed QA to the function, we need Q times delta. In passing, we note quickly that the application does nothing useful with the modality context. Let's now look at the introduction and elimination rules for qualified types. The introduction rule works as we said before, namely, we multiply the context by P. The elimination rule is a bit more involved. Note first that we assume that little gamma produced PA. Now, we want to use this A to produce C in a continuation. We could think that we'd have PA in the context of the continuation, but instead, we are allowed to multiply by an additional arbitrary Q modality. This is because to produce one C, unit C, we may need another modality within exactly P for A. And thus, this version gives more flexibility to the programmer. On top of this, we also have an order on modalities, and it is generated by a semilattice, a mid-semilattice. This order drives the weakening rule, as shown here. We can also see the converse, and this is a conversion rule from P to Q if P is less than Q. The exact structure of modalities is as shown here. pause the video, or you can check out the paper. But the interesting bit is the last line, namely that addition distributes over meet. This property also implies that addition is monotonous. We can instantiate the structure to various special cases and obtain several useful systems in this way. First, we can do linear types. 0 and 1 acts as you'd expect. We just need to add the modality omega to support unrestricted usage. That's the bound modality in linear logic. The rest of the structure is as you'd expect, and omega is acting as a catch-all value. A useful generalization of linear types is as a system which tracks the exact number of times that a variable is used. However, one must allow for sets of possible usages to implement the need as set union. The rest of the structure falls out from this choice. An interesting property of all such model systems is that a zero annotated parameter is guaranteed not to be used. This is captured by the irrelevance theorem, which is stated as shown here and proven in the paper. The lattice, which, as you recall, corresponds to the order of modalities, can be used for various purposes. It can be used for security purposes, with more secret levels towards the top. It can be used to represent the necessity modality, with more necessary propositions towards the bottom. It can represent levels of beliefs. More credulous agents are at the top. It can represent computational relevance, with more relevant types toward the bottom. Remember that convertibility is from bottom to top, and so at the meet of P and Q, all data which is available for either P or Q is also available there. We can now take a moment to ponder what happens when one does not care about quantities, and so modalities are only used to represent levels in a lattice, such as shown previously. In this case, the meet becomes the addition and the join becomes multiplication. Additionally, 0 is also the top of the lattice. A consequence is that to produce 0A, or really top A, the modality context can be ignored, and so we can use all variables, even those that are available with modality 0 in delta. A last application where precise quantities are tracked is sensitivity analysis, which you can read about in the paper. Let's now turn to the meta theory. We consider first operational semantics, whose cornerstone is the substitution lemma. The proof follows the usual structure, but we have additionally to express how modalities are transformed by substitution. It turns out that the modality transformation applied by a substitution, here sigma, is a linear operator, here psi. The proof is straightforward, but it is interesting to note that the requirements necessary for modalities correspond exactly to the modality structure, which we have shown previously. We also have a modality-preserving abstract machine. This is a call-binding machine where every state is well-typed and well-qualified. The main point of showing this machine is to show that dynamic execution steps will never overconsume, underconsume, see private information, etc. So the modalities annotations can be realized at runtimes as such. Finally, we have a relational crypt case style semantics. We interpret types by relations, and these relations are indexed by worlds. The main novelty here is that we can interpret the PA type by a notion of division, or more precisely, a Galois connection. For quantitative systems, W is a multi-set of resources to consume. P is then interpreted as a natural number, and to interpret PA at a world W, we interpret A at a world W divided by P. For non-quantitative systems, W is a set of capabilities. Types are indistinguishable if the associated capability is not in W. We can take advantage of the fact that every modality can be represented by a set of capabilities. So, to interpret PA at W, we interpret A at the world, which is the difference of the sets W and P. Combining the two views is somewhat tedious, but it is shown in the paper. A perhaps controversial choice is that we have a constraint on which modalities can a value take to be scrutinized by a case expression. We demand that they must be convertible to the unit modality. This constraint is necessary for irrelevance. Otherwise, we will be able to see if we are on the left or on the right of the sum for every modality. And then everything becomes observable at every level, even 0. But the operational semantics do not, in fact, rely on this constraint. And so there are other choices. There is an extended discussion of this topic in the paper. Additionally, in the paper, we deal with the whole of system F, of course, with sum and products. And we have quantification of modalities, which means that we have higher order model types. We also show more applications of free theorems, and we also give a wealth of nice details, so feel free to check it out. In conclusion, we declare victory because many useful systems can be captured by our framework, and it has indeed a rich meta theory. As future work, it could be useful to describe an application which exhibits a non-commutative multiplication. All those that I have shown so far don't. Another useful development would be to have a representation theorem for the modality structure. Thanks for watching.
Thank you, Jean-Philippe. At this point, please make sure to join a Q&A session if it is available in your time band.